We are going to journey to the world of synchronization at Industry 4.0, where distributed telemetry systems are more tightly dependent on each other than today. My name is Tomasz Widomski and welcome to ELPROMA ITFS presentation. Along a way of being 30 years in industry, finally ELPROMA is approaching Industry 4.0 at a very new facility located in Poland, where there are new labs equipped with atomic cesium clocks. In this presentation, we will try to point the importance of the future synchronization in Industry 4.0 and its relation to current known Industry 3 application we all well known. The fourth industrial revolution introduced a new concept of smart factory, where existing M2M telemetry systems are linked together with a new generation one. There are more distributed autonomous IP sensors and data processing, and the smart factory learns from it what is going on now and how to ensure best efficiency of operation in the next step of smart factory maintenance. There are less moments that in the past the factory can fail or accept even the short temporary hold of operation. Such automation process is going to amplify, evolving in time, and therefore there is already requirement for testing a new technologies like a human cognitive cyber one. In a long way of time, what we recognize today as a modern telemetry, it will stay linked, creating a global connectivity system-to-system class IIoT architecture. To keep all this in order, the telemetry data processing looks already for high resolutions and for high accuracy time domain operation. In case of big data and machine learning, the high accuracy frequency domain is going to play important role too. The very good example are new single photon technologies at telecom, especially a quantum cryptography that exists already now. So this is why currently a new time-sensitive networking TSN technology is introduced, and more devices are following this new industry standard. It helps create the safety margins for optimization management, the very important key factor for Industry 4.0. The concept of distributed system is becoming to be important. The distributed system can be neither a group of telemetry sensors working together or a big cloud where stored data is divided to small subparts archived in different places. A distributed system technique is even used inside your car today. The scenario is sense and read remote data to set a state, then predict the next state, and make the correct presetting to appoint your predictions. At the real-time system, the GPS clocks were fine for over past 2 decades. However, now some new aspects of understanding UTC needs to be taken into account, since this timescale is not as universal as it sounds. In fact, each country produces its own UTC that is tiny fraction different from others. And besides maintaining a large volume of GNSS receiver that is not easy, it's bizarre, UTC from different satellites system is different too. The fourth industrial revolution is all about improving efficiency and operational robustness. The smart factory needs to ensure operational continuum frequently 24 hours a day. Whatever goes wrong, the smart factory cannot stop and needs to predict the next steps according to emergency or replacement plan. This means that important to highlight is the predictive maintenance of smart factory, and that creates complex multi-level structure of this slide. The requirement of accuracy of each node is different and it depends on industry, but it will evolve in time to high accuracy, and therefore assuming a single microsecond accuracy of synchronization at each node is acknowledged. The system is simultaneously receiving a lot of data from many different sensors. Some of them operate autonomously, and they are what we call the smart IP sensors. In many cases, sensing data real-time is requiring the sensor fusion. This is a kind of synergy if a different sensors provide a single unified complex data output. Sensors produce large volume of big data that goes via IoT and Industrial Internet of Things, first goes to the edge, then to cloud. And that means data is maintained in one or multiple data centers, including fog computing. The new artificial intelligence algorithms are involved and need to be taken into account when considering next step the real-world system interaction. The real world means the change in time that needs to stay frequently coherent to human being perception and to its physical activity reaction time. So where we go finally to achieve the target process automation, it is a real time, and in many cases it creates the complex domino chain of relations between factory, its suppliers and customers. At least several nodes of Industry 4.0 data flow are well known how to build a robust synchronization today. Let's quickly see the examples of existing markets and how they correspond to Industry 4.0 nodes. The data centers, especially MiFID II financial market and banks, they currently use NTP for decades. Now, successfully, they are transferring to precision time protocol. The public administration, it has been already delivering trusted cryptographic timestamping to ensure no repudiation of e-documents and certification. The telemetry machine-to-machine communication, together with the big data blockchain and machine learning, artificial intelligence, and new algorithms, they are now in tests of smart city maintenance. Autonomous vehicles, car platooning, traffic control, both air and railway, they are the solution that exists and has stable synchronization today. And the last but not least, the most important one, two industries. The fifth generation telecom, representing well and deep understanding of synchronization importance, delivering EPRTC, but shortly transferring to coherent network PRTC clocks, and the distributed smart grid system, ensuring future power stability. There will be no stable, good performance, high efficiency Industry 4.0 without 5th generation telecom and smart grids. When we look to Industry 4.0 from the ground floor, everything seems to be disordered. Looking from 3D level, the scope of Industry 4.0 seems to be much more clearer and better understandable. When all synchronized, the right safety margins of performance are ensured, making Industry 4.0 stable and robust. Synchronization seems to act here as a conductor of orchestra. The sound is good and the music is perfect, if such conductor will continuously do a right job. This is why the importance of synchronization is increasing and evolving in time. The challenge is not limited to fact of improving accuracy, but mainly it is all about keeping stability of time and frequency domain. Here comes several new risks and challenges. The main is the challenge of developing standard unification, that it is what the TSN brings to market. But secondly, it is even more important to ensure a cybersecurity. Here, like never before, the risk and the resistance for the time synchronization attacks like the GNSS jamming or spoofing is important. It is because it can trigger a domino chain reaction. In case like a smart grid, it might cause a serious large-scale infrastructure failures, including blackouts. Before we dive deeply to niche aspects of cybersecurity of synchronization, let's define a simplified block diagram of Grandmaster. Here is what you need as the minimum. There is a GNSS receiver providing the reference UTC time and date information. There is also the computer and the network interface card. Together with NTP and PTP software stack, this is all you need. Just in case of GNSS receiving problems, the internal or external oscillators are used to perform holdover. Devices mostly also support the frequency output that goes via simple clock processing unit. The advanced EPRTC is focusing on the long-term average measurement, deploying steering of frequency and adjusting phase to UTC. Here, a single detail is important, including the most important one, the control over the temperature. So what are we afraid for? Let's define only two general problems to point today. First of all, we all believe to know how clocks operate. It is because our intuition says it is simply not possible that ordinary mechanical wall clock can suddenly jump several minutes or hours forward or backward. This is all wrong, because inside computer time is represented binary, and any firmware arithmetic overflow will cause its instability, providing frequently very large time errors. Let's focus on GNSS receiver. A lot of people believe that accurate time comes automatically from satellite vehicle. This is partially correct. Time information is included inside telemetry received from space. But the real accuracy and even more important, the stability of UTC born here on Earth inside the GNSS receiver. So currently this is why the UTC from different receivers can be different too. This is the level of tiny fraction of single microseconds only. Furthermore, the time differences can depend on the receiver model or even depends on the specific firmware version. This problem can be gained when for example, UTC leap second announcement is received, or proceeding extraordinary events like 2019 GPS week number rollover, or 2016 internal GPS error of SVN23 that introduced 13.5 microsecond time error. This is improving risk of internal GNSS firmware overflows, but also a different algorithms of each firmware will proceed events on a different way. There are some known cases where a leap second announcement has triggered large time errors, counted hours or even date errors. That sounds here a bit ridiculous, but it's true. Surprising is that using multiple GNSS constellations simultaneously, it is mostly not improving the accuracy of UTC synchronization. Currently, the best accurate receivers trace a single satellite in common view mode or using active two-way satellite time and frequency transfer. Besides, each GNSS subsystem bases on a different internal timescale, where the GPS-T and the Galileo-T are 18 seconds ahead of UTC, Beidou-T is 4 seconds ahead of UTC, and GLONASS is just following the UTC. The natural offset between GPS and GLONASS floats up to 40 nanoseconds. This sounds not much, but already today this is a 20% of target PTP accuracy when considering a modern distributed smart grid system IEEE C37.238. We also want to highlight that the timescales are independent of each other, and therefore the random errors can be introduced anytime. A good example is again the 13.5 microsecond of SVN23 dated January 2016. This specific problem was giving a different results depends on the receiver and device we test. The 13.5 microsecond is large error. It cannot happen again to Telecom 5 generation or to future modern smart grid systems. Finally, the GNSS jamming and spoofing risk needs to be taken into account more than ever before. The impact of jamming can be limited by using special active filter built into level 1 smart antenna or available as a level 2 rack mount device. Spoofing can be detected too by GNSS receiver inside smart antenna triggering the alarm line to switch protected device to holdover mode. In many cases, level 3 GNSS simulation, frequently called the GPS firewall, can be considered for extra protecting the critical infrastructure. The level 1, 2, 3 are available from ELPROMA today. But frequently the simple solution are the best effective one. Here, the replaceable GNSS modules with various of different GNSS receivers on single standardized board is perhaps the most simple and inexpensive way to start working on robust synchronization at Industry 4.0 systems. There is never enough time to talk about every single details of security at Industry 4.0 and especially of synchronization related one. Today we have pointed some weaknesses of time gaps related to GNSS receiver side. But there is much more to talk about the synchronization security when considering complex system-to-system relation at Industry 4.0. This is the last slide we have prepared today. There are some nice and large projects there. ELPROMA is co-developer and or contributing. We would like to thank you so much for so many years spending together. Thank you.